the assignment too. So in the IP regulatories and reimbursement part, do I also mention the ISO standards, or is only the regulatories enough, the classification and all?
Yeah, you don't need to look at the standards necessarily. No.
All right.
Yeah, unless that's sort of relevant to the approval.
Okay.
So for medical approval, you'll usually need to be compliant with ISO 3485 or something like that. So that will be part of the process of the regulation.
There's a general one for the medical devices. Maybe I'll include that.
Yeah, so just mention that as part of the process of gaining approval, you need to be compliant with those standards. Yeah, or approved. So guys. All right, ready. Cool. So today we're going to be talking about X-rays. I'm going to do a little bit on ultrasound as well at the end, and also I'm going to recap some of the stuff about fluorescence because I didn't explain it very well last week because I had to rearrange some things around. So this is a silent film from 1897 called The X-rays. X-rays were formally discovered in 1896. So you can see sort of how quickly it sort of captured the public imagination. They made this film. Also interesting about this film, it's one of the first uses of special effects. So they did some fancy editing to kind of make it look like you're see-through. Yeah, so that's just a nice little film. And so X-rays became pretty popular pretty quickly, and we'll see sort of about that later. So first I want to revisit some things. This will be important for your understanding of X-rays, how they're generated, and how they sort of interact with matter, and also for fluorescence. So I should have done this before, but I'll do it now. So basically, you've all done high school physics, so we can think of an atom. Matter is made up of atoms. We can think of an atom in a very simplified way as a nucleus and some electrons. These electrons exist inside energy shells, so they have a certain energy level, and they're discrete energy levels, so they don't exist in other, they exist only in these discrete levels, they don't exist in between these levels. So, energy levels, right? So photons have energy. When matter absorbs light or emits light, it occurs that there's an energy transfer because we have photons of energy coming in and they get absorbed. And that energy transfer occurs in the electrons. So these electrons can jump to higher energy levels or lower energy levels. If they jump to a higher energy level, then the photon's been absorbed. And if they jump to a lower energy level, they'll emit a photon. So they'll emit light. Now that jump will only occur if there's a gap between energy levels that is exactly equal to the energy of the incoming photon. So that's why some materials are transparent, because most of visible light, there's no energy gap for it to absorb the light, so the light just passes through, the photons just pass through. You can't absorb them because there's no energy, the electron can't jump to an energy shell which is equal to that gap. Okay, so let's talk about fluorescence again. So hopefully you can understand this a bit better than last week. Essentially, this is what's happening in fluorescence. We have light of a specific energy coming in, and there's a specific energy gap between energy electron shells whereby it equals the energy of that photon coming in. The electron can jump into a higher energy level, so it's in an excited state. It's absorbed some energy, some blue light. Then it relaxes a little bit, it might lose some energy due to heat, falls back down to its ground state. So it loses energy, and that energy is different to the energy that it absorbed because it's lost some. So it's a lower energy. So it emits light of a different colour, green light. So that's the process of fluorescence. Now, I've got a demo actually of fluorescence. So this is what I want to show you. And this will show you, hopefully, I'll shut the door. This will show you also why fluorescence is so good for imaging. All right. So I've got this little guy, right? Glow in the dark, little dinosaur. It's not emitting any light. Wish I could make it darker. Maybe I can turn off all the lights. Nope. All right. Anyway. This is a UV torch. So it's not really giving off much light that you can see. UV light. We don't really see it. There's a little bit of purple there, but we don't see it. But if I do this, now this is glowing. You can see it glowing. It's glowing green, right? This is UV. Now this is glowing green. You can't really see the light coming off here, but this is fluorescing extra light. This is fluorescing light at a different energy level that we can actually see. And so that's when we're imaging, we're doing fluorescence imaging. It means we can just sort of only see that. We don't see the emission light, or we can at least filter out this light. It's giving off light of a different colour, a different wavelength. So that's basically fluorescence, and that's why it's so good for imaging. We can filter out this light, we can filter out any other light, and all we get is the emitted light, the light emitted from the sample. And that's exactly the same process as what's happening mostly the same process as what's happening in fluorescence and fluorescence imaging. This is just on a longer time scale, so that'll still glow after. Anyway, okay. So hopefully that was a bit helpful for fluorescence. So today we're going to move on from optical imaging and talk about X-ray imaging. X-ray is the most kind of common medical imaging modality. We learn about how they're generated, some sort of characteristics of the source, the X-ray sources, some emission spectrum characteristics. So that means the frequency spectrum or the energy spectrum of the X-rays, detection, resolution, and how we form images using X-rays, and how that sort of relates to actual practical cases. And then after that, in sort of the next hour, we'll talk about ultrasound, how it works, and some applications as well. All right, so where am I going? So what is medical imaging? So imaging of the human body. and it's for medical purposes, so diagnosis, monitoring of pathology. We can get details of the shape and structure of the organs, so how they look, and also we can get details of how organs are functioning as well, which is sort of added value. Various modalities, we're going to focus on X-ray and ultrasound, but there's also PET and MRI, which you've probably heard of, but we won't talk much about them. So this is just a bit of an overview of those that I just mentioned. And you can look at this sort of in your own time as well, but basically X-rays use absorption contrast for medical imaging. There is other types of contrast, which Kay will talk about in her guest lecture, called phase contrast, but talk about absorption contrast here. You can look at bones, look for breaks, look at lungs, things like tuberculosis and pneumonia, fluid in the lungs. You can look at cardiovascular system. It's high resolution, it's pretty fast, it's a known quantity, it's pretty cheap, relatively cheap. And the disadvantages are that there's dose, radiation dose. We'll talk about that in more detail later. Ultrasound is using echoes of ultrasonic pulses, so pulses of sound at a higher frequency than we can hear with our ears. So it's not electromagnetic spectrum, it's pressure waves. Advantages of that, they're portable, they're cheap, and they're very safe because there's no ionizing radiation, no dose. And disadvantages, it's pretty low spatial resolution, and you can't image through the lungs or the bones. And we'll talk about that a bit more too. So magnetic resonance imaging uses the spin of the poles in the atoms of your body. It's pretty technical, and it's really good for soft tissue because it can look at the sort of the proportion of hydrogen atoms in different tissues. So it gets really good soft tissue contrast. It's very, very high resolution as well, sort of similar resolution to X-rays. It's got no X-ray dose, no radiation dose, but it's pretty expensive, and also the scan times are quite long, so of the order of minutes, rather than seconds for X-rays or less than seconds. Also, it's pretty uncomfortable, very loud. I don't know if anyone's ever had an MRI, but they give you headphones, try to play music to you, because it's loud and uncomfortable. You're in a little tube. And also, if you have any implants that are metallic, you can't put anything, you can't have anything in the room that's metallic, or it just gets picked up by the huge magnets and thrown through the bore where you're sitting. So, yeah. And I've put a video on Moodle as well of that happening, so have a look at that. It's pretty cool. PET and SPECT are based on introducing a radionuclide, so a radioactive material, into the body. And you can see the gamma rays that are thrown off by that radioactive material. They can tag that to glucose, which means that they can look at metabolism. And it's really good for looking at cancer, because cancer is just cells that are metabolizing too fast. And so all the glucose goes to those cells, and they just light up on a PET scan. And that's sort of the main use of it is for cancer, for PET anyway. And disadvantages is expensive and long scan times as well, and there's some practical difficulties in the radionuclide side. So that's just an overview, and we'll get into X-rays and ultrasound a bit more, and definitely X-rays right now. Okay. Yeah, sorry about that. So a bit of history. 1896, Wilhelm Röntgen published his paper called A New Type of Ray, which was essentially, it was describing X-rays for the first time, formally. And that's a X-ray of his wife's hand, and you can see the ring, you can see the bones there. I mean, this would have been just amazing at the time. 1896, there was no powered flight then, pre-World War I, all that stuff. So, pretty early days, and it just really would have been completely magic to them. And as you can see from a year later, they had silent movies about it. So X-rays are radioactive. They're ionizing radiation. So they're very high energy on the high end of the electromagnetic spectrum, which I showed you in my first lecture. And what that means is they can strip electrons. They have such a high energy that when an atom absorbs that energy, that high energy photon, the electron can actually leave leave the atom, and that creates free radicals, can damage DNA and cause cancer. It's a real risk, and any time an X-ray is used, there's a risk-benefit analysis done, or a weighting done before it can be used for a certain application. We all get radiation dose every day. There's radiation everywhere, emitted from the ground, in bananas, cosmic radiation. Average background radiation is about 2 milligray a year. This is 2.5 a year. A chest CT is 13 milligray, so quite a bit higher than average, than your average annual radiation. A cardiac CT angiogram, which we'll look at as well, is 40 to 100, because that's like a video. And so that's pretty high. And the only reason, you don't do that unless you have a serious problem that, this will save you from a heart attack kind of thing. So that's just a bit of background on dose, and that's sort of, think about that when you're looking at some of these videos I'm about to show you, and also there's always this, with any medical imaging, there's always, and with any medical intervention, there's always a sort of a risk versus a benefit. Sometimes these aren't fully kind of appreciated, so yeah. Alright, so now I'm going to play a movie, hopefully the sound works.
Late in 1895, in a little university laboratory in Bavaria, Professor Wilhelm Conrad Röntgen first noticed the strange effect which led to the announcement of his discovery of X-rays. And although the news was received by the public with a mixture of disbelief and apprehension, doctors immediately saw the possibilities of the mysterious new rays and began to use them. It was not until 1913, however, that their use became certain and reliable. In that year, the hot cathode X-ray tube was introduced by Dr. William D. Coolidge of the General Electric Research Laboratory, the man who had already developed the all-important ductile tungsten lamp filament, and who now holds one of the world's few honorary degrees of Doctor of Medicine. In speaking of X-rays, therefore, it is a privilege to be able to present Dr. Coolidge himself.
For a long time, after X-rays were discovered and used, they remained a mystery even to the scientist. That is how they got their name, X for the unknown. Today, however, we know that X-rays are a form of radiation belonging to the same family as light, heat, and radio waves. We know also that X-rays are produced whenever a solid target is struck by a high-speed stream of electrons, those same little negatively charged particles of electricity which make our radio tubes work. In early X-ray tubes, the electrons necessary to produce the X radiation were released by first breaking down a small amount of air or other gas in the partially evacuated tube with high voltage applied between the terminals. Operation depended upon the amount of gas within the tube, and since this was variable, the tube was unreliable. In the present day hot cathode X-ray tube, of which this is one of several different types, there is a high vacuum, and the production of electrons depends only on the size and temperature of an incandescent tungsten filament with a cup-shaped structure surrounding it. This particular tube has two filaments, either of which may be used. The swarm of electrons, which is liberated or boiled off from the white-hot filament, is speeded up to a very high velocity by high voltage applied between the negative electrode or cathode, which carries the filament, and the positive electrode or anode, which is called the target. The electron stream is focused to a very small spot on the target by the cup-shaped cathode structure. It seems that the electron stream striking the target at terrific velocity is stopped so violently that the electromagnetic radiation known as X-rays is produced. The efficiency of X-ray production is very low, and most of the energy of the electron stream goes to heat the target. This heating effect of the electrons may be likened to the flame of a blowtorch striking a metal plate, while the light coming from the heated spot on the metal plate target corresponds to X-rays coming from the focal spot on the target of the X-ray tube. As a matter of fact, X-rays are like ordinary light, except that they are a very much shorter wavelength and are therefore invisible. Although X-rays themselves cannot be seen, their effects can fortunately be made visible. Photographic film in general is sensitive to X-rays, and a special type of it is used to record their presence. Recording of X-ray images on film is called radiography, and the finished films are known as radiographs. X-rays also have the power to make certain chemicals fluoresce, that is, give off visible light. A piece of special cardboard coated with one of these chemicals constitutes the so-called fluoroscopic screen. The use of such a screen to reveal an X-ray image is known as fluoroscopy. It has the advantage over radiography of enabling us to visualize internal structures in motion. Besides being of much shorter wavelength, X-rays also differ from light rays in that they cannot be focused in a camera. So ordinary photographic procedure cannot be employed. Instead, we use a shadow technique. If I now turn on this small spotlight and place my hand in its beam, I can cast a shadow of my hand on a white card. Now, if instead of the spotlight I use an X-ray tube, such as there is in this little portable X-ray unit, and if instead of the white card I use a film in a light-tight holder, I can cast an X-ray shadow of my hand, which on the developed film looks like this. Note, however, that instead of a solid silhouette shadow, as with light, the X-rays produce a shadow which shows a distinction between the bones and the flesh. In other words, X-rays pass through some substances more easily than through others, and the details of the image depend upon the amount of X-ray getting through the different substances which make up the object. It is this ability of X-rays to differentiate between types of substances which gives the rays their great diagnostic value. It seems both incredible and paradoxical that rays which are themselves invisible can reveal objects which are otherwise also invisible. But that is exactly what X-rays can do. It is then no wonder that X-rays have, in less than half a century after their discovery, become so useful in medicine and industry.
All right, so that gives a pretty good sort of summary, I guess, of what I'm going to talk about. Yeah, so some interesting things to note there that you'll see later. He said X-rays can cause some materials to fluoresce. What else did he say? That's probably the main one to take note of, I guess. Anyway, so basically, X-rays are formed with a cathode tube, same as sort of like what's in your television, I guess. So we've got a cathode, your old television, or your new ones. We have a vacuum tube. Yeah, I'm old. I had a cathode ray television back in the day when I was a kid. So we've got a cathode inside a vacuum tube. So and we have an anode, and we put a high voltage across there. That cathode is often a tungsten cathode, and that's going to provide some electrons. They're going to go sort of accelerate towards the anode. There they go. So the voltage gives them really high, gives them energy, gives them kinetic energy. So they become, energized, and they accelerate towards the anode. And then that energy that they've gained is given off through certain processes, which I'll go into after this slide. They give off X-rays. And we have a little X-ray window potentially here to let out some X-rays there. And that's basically it. So the voltages range somewhere between 20 and 200 kilovolts, something like that. And that's it. So why does these X-rays come out when you hit the anode with the electrons? So it's a question. Now there's two types of X-rays that are produced. The first one is called characteristic radiation. So here we have a tungsten atom. And again, just our very simple kind of, really simple model of an atom. We've got a heavy proton here. Sorry, a heavy nucleus. So 74 protons in tungsten. We've got some electrons whizzing around in their electron energy shells. We're going to introduce an electron. So this is an electron coming in from the voltage. So this is an electron that's being produced from the cathode, accelerated towards our anode. So that's a high energy electron coming in that's going to be introduced. Now that's going to interact with the electrons already there, and it's going to strip that out. They're going to repel each other because they're both negative charges. I'm going to lose that electron there from a lower energy shell. So we've lost an electron from our atom. Now that's going to be a little bit unstable. We don't want to have lower energy electron shells that aren't filled. So what happens next? We've got our empty shell. So then this guy is going to drop down to fill the void and give off an X-ray. It's losing energy, it's dropping an energy shell, it's giving off photon, and that photon is of an energy which makes it an X-ray. Now, what do you know about this X-ray that's going to come out, this photon? What's the energy of this photon going to be? Yeah, it's going to be specifically the energy that equals this energy gap between the electron shells. So that's a very, very narrow band. It's a specific energy. So colour, think of it as colour. It's a specific colour that's dependent on the makeup of the anode, and the electron shells in the atoms of the anode. That's one type of X-ray that comes off, and these happen both at once. Then we have another type which is called Bremsstrahlen. Bremsstrahlen is just German for braking. Braking as in braking your car. So the anode has 74, it's a heavy element, and so it has a lot of protons within the nucleus. Tungsten has 74 protons. So as an electron passes into the anode, it's going to basically interact with those protons. It's going to decelerate. It's going to be attracted to them. It's going to kind of slow down. It's going to be braked. It's going to break. And it's going to lose energy in that way. It's going to lose kinetic energy. It's decelerated. And you can't just destroy energy, so that energy is then given off as an X-ray. Also, there's going to be some given off as heat. Actually, quite a lot as heat. Now, this bremsstrahlin is not dependent on the energy shells, on the electron shells of the atom, and so it's a more broad band. It can be of, a continuous sort of spectrum of different energies, depending on, various things like how close it's going to be to the atom, and sort of factors like that, how much heat was given off, how efficient the process is. So it's sort of a broad band. And so this is what the spectrum of a tungsten anode looks like. Where's my little guy? So on the x-axis, we have photon energy. This is the X-ray energy. It's expressed in kilovolts, sometimes also expressed as kilo electron volts. So that's the energy of the X-rays. You can see there's a spectrum. So the radiation that comes out is always sort of a broad band of different energies. And this is just the number of photons, the flux, essentially. This here is the bremsstrahlin. So we have this sort of broad band. The peak is lower, but there's a lot of it because the number of photons is actually the area under this curve. So bremsstrahlin gives off a lot of energy, a lot of sort of flux, and it's a broad band though. It's across that wide range of different energies. And then we have these K lines. This is the characteristic radiation. It's a very narrow band of X-ray radiation. Across a very tight band of energy. Within that energy range, it's very high, but the area under that curve isn't that high, obviously. Now, the characteristics of the X-ray tube will determine the exact makeup of this spectrum. The K lines, where they are is controlled by the anode material, so you can't really change them, but you can change the voltage and the current of your tube. So the voltage is, you think of it as it's what's accelerating the electrons, so that's giving them energy. So that can change the energy. So if you up the voltage, you're going to give more acceleration to the electrons. They're going to be higher energy when they hit the anode, and then your maximum energy of your bremsstrahlin can be higher. So that means your X-rays will be a higher energy. They'll more easily pass through the body, and we'll talk about attenuation later and contrast. Current, if you up the current, so the number of electrons that are being incident on the anode, it controls the number of, or the intensity of the X-rays coming out. So not the energy, not the colour, but it changes the brightness, essentially. And brightness will affect signal-to-noise ratio, and also will affect dose. If you have more flux, more photons, then you have more dose. And image brightness is important because you have a noise floor on your detectors. So a brighter image is just more signal, hence your signal-to-noise ratio improves. So that's how you can control the spectrum, and these are the parameters which control the characteristics of the image that you're going to get out. This shows two spectra, one of 100 kilovolts. So this is the energy that's given. It's not the photon energy; it's the voltage across the anode and the cathode. So you get 100 kilovolts, you see a brighter peak, brighter X-rays. Because they've got more energy, you can give off more. The maximum energy is more. The K lines are in the same place, but they're higher up. Okay. So let's talk about electron focal spot size, because this determines our resolution. These electrons don't all hit in the one space on the anode. They hit across an area of the anode. And so X-rays are being produced across a certain area of the anode. The size of that area, the spot size, the focal spot size, or spot size we call it, determines your image sharpness and your spatial resolution. So if we have a very large spot size, and we do some ray tracing here, so there's X-rays coming off this whole thing. Look at one's just coming off the edge, and incident on this edge casting a shadow. You know, this one will hit our detector here. This one will hit our detector here. And so that edge is spread across this whole area. We get a blurrier image. Small spot size, sharper image. Yeah. So I'm going to do a demo of that potentially. So think about it as when you're a kid, you're doing shadow puppets. If I use my phone now, this has got a LED in it with a very small filament in it. So essentially all the light is coming from a very small spot. I'm going to get a very sharp shadow. So it's pretty sharp, I've got a very small spot for a sharp shadow. If you look at the, if I turn this off and we look at all the ambient light, you can't even see it, but there's a very kind of dull shadow there, a very blurry shadow. Because the light's coming from all directions, it's not casting a sharp shadow. It's the same thing here. If you have a large spot size, you've got a very diffuse light source, you get a blurry shadow. The sun casts a very good, the sun's very big, but it's very far away. So that casts a really nice shadow as well. But this light here, it's pretty good, but yeah, so anyway, that's basically what's happening here. Now, I mentioned that some of the power or the energy of those electrons hitting the anode is converted to X-ray, some is converted to heat. Actually, most of it is converted to heat, 99%. So if I have a really small spot, I'm concentrating all that heat in a really, really small spot, in a really, really small amount of material on my anode. It's going to get really, really hot. It's like using a magnifying glass to start a fire. It's putting all that light into a little spot, and your anode will actually melt. So this puts a limit on how much energy, how much power I can put through my system for a certain spot size. So if we have a large spot size, we can have a brighter source, because we can put more energy into it. The heat's dissipated across a larger area, but I have my blurry image. So there's a trade-off there. And you can't get really high resolution imaging, really sharp images, with really bright sources, because you just melt your anode. For a stationary source, where the anode is just stationary, it's a real problem, but what someone decided to do was, let's move our anode around, and then we can dissipate the heat across a wider area, and we can have a much higher power for a small spot size. And so that's what they did. This is a sort of an old rotating anode, but it's good because it's glass, so we can see inside. So basically, we have this rotating anode now. This is the cathode. This is where the electrons are coming off. They're focused down onto this point here. And so X-rays are going to come off this way. And what we do is now we rotate. This is a disk, and so we rotate that around. And so now the electron spot is sort of being swept across that anode, and so there's more area and it allows time to cool. So we can get much higher power through rotating anodes to give us a smaller spot size for the same power. So we can, yep. They rotate thousands of RPM, so they're really quick. And it depends on the model. But these can get something like they're 100 times brighter, like they're serious. So most sources now would be rotating anode sources for medical imaging, but obviously they're much more expensive. Yeah. Okay. So that's generating the X-rays. Now, how do we detect them? You saw the film on the video. Now, that's pretty old school, and it's not really used much anymore. It's pretty insensitive, and you want something pretty sensitive because why? Why would you want a sensitive detector? Yep. Another reason? Dose. If it's not sensitive, you've got to put more light through, you've got to put more X-rays through, and you're just going to up your dose. So you want to make the most of the dose you're putting through. So we don't really use these anymore. Poor Kodak. There again. Gone out of business. All right. So I mentioned, or Dr. Coolidge mentioned, that X-rays will make some materials fluoresce visible light. And this is how we detect the X-rays in medical imaging. So we have what's called a scintillator, or a phosphor, often called. And so this phosphor will actually glow when you hit it with X-rays. You can see it with your eyes, but if you have bright enough X-rays, but it's glowing. And then we put a CMOS array on the back of that to detect that glowing light. It's that simple. So these are flat panel detectors. You're casting a shadow, so you need a big detector to see that, to capture that shadow. This is what's called a structured scintillator. You can see that here. The crystals within the scintillator are grown in the sort of directional vertical pattern. So that means that it acts like a bit of a fibre optic, and any light which is fluoresce from this point will be guided down onto that detector, onto that pixel. It's a CMOS pixel. So that means that we can have a thicker scintillator without having a blurry image. So we can maintain some sharpness, some resolution with a thicker scintillator. Thicker scintillator will be more efficient. It will detect more of the X-rays. It will fluoresce more, capture more fluorescence than a thin scintillator. And so this is sort of the standard now is a structured scintillator. Previously you'd have a powder scintillator and they just sort of spray powder across a phosphor material, and this means that you get this diffusion. Any light here is going to go off as a source in all directions, and you'll get a blurry image. So that's a flat panel detector, and that's the main kind of medical imaging detectors. So that's great, but one thing's missing, or one thing's different to our optical detectors, and that is, so I spoke about resolution, the spot size. We want a small spot to get that resolution, to get that sharp image. What's the other type of resolution? The sensor resolution. And this doesn't allow for any magnification. The image that you create there is just the image, it's just the shadow of your object. So how do we magnify? What if we want to see something that's smaller than our native pixel size here? Well, we can magnify the shadow by using geometric magnification. It's just a schematic of that there. We have a source, we have our object. This is an imaging system. We have R1, which is a source object distance, and R2, which is an object detector distance. There's just an equation here. It's a ratio of the total length to the source object length. Gives us our magnification. So this allows us to magnify our shadow, and it can change our sensor resolution. And now I'm going to do another demo as well, because I like to do demos. See if this works. So this is my X-ray source. This is my detector on the wall. And that's my shadow. So it's that size. So imagine I've got a detector there with an array of pixels. It's going to be sort of, the effective pixel size will be dependent on the magnification, and that's there. So if I move towards the source, it gets bigger and bigger and bigger. So I'm magnifying that shadow. And that's how we can do magnification. I go closer and closer. It's small. Right? Now it's the size of the object. And that's how we do magnification. So if I have a shorter source to object distance compared to the total distance, then I have higher magnification and I'll have higher sensor resolution. Hopefully that makes sense. Alright, that was my demo. Alright, so there's other ways as well, and we do this in research. We have different ways. If we want to get some more magnification, we can use a lens coupled system. So we can take our scintillator off the detector and put a lens in front, a magnifying lens, and that's what we do here. Often we do this at the synchrotron, and we put a microscope objective lens, and we can get sort of micron resolution. So you have your scintillator, it gives off visible light, you focus that down onto your CCD or CMOS. So essentially you've got an optical imaging system and you're taking a photo of the scintillator, which is now glowing from the X-rays. You can do demagnification with this as well, which can be handy. You put a mirror in there because you don't want the X-rays sort of burning out your CCD. You want to keep them away from your CCD. Some of the X-rays will continue through past the scintillator. another way to do it is use a fibre optic taper. So we'll put a fibre optic in between our phosphor, our scintillator, and our detector, and it's tapered, and that gives you a demagnification. So if you want to use a certain CCD chip that might be sort of super low noise or super fast CMOS or something like that, but very small, you want to magnify, you want to maybe demagnify there and get that area onto that little chip, and so that's how that works. All right, so now I'm going to take you through an experiment that we used to do in the course, but we can't do anymore because there's too many students. And this is actually an exercise which we did last year, which was a prac. I'll put it up on the Moodle. You can go through it as an exercise if you want. I'll put the result, the answers, up as well. But yeah, we'll go through a little bit of it now. So basically, what if we want to measure resolution? I guess we can measure resolution just using a phantom. So that's what we did. We got a resolution phantom, a line pair phantom. We have our X-ray source. This is a really specialized X-ray source with a liquid metal anode. Why would we have a liquid metal anode? What can't a liquid metal anode do? Can't melt. Also, we can pump it, and we can have a heat exchanger. And so we can get really, really small spots for spot size for really, really high energy, get really, really high resolution. There's only one company that makes these from Sweden. They're about 0.5 mil each. We had 3. We've got 1 now. So basically, I took an image of this resolution target. R1 plus R2 was 3 meters. I won't tell you the R1 and R2 distances. We used a PACScan 2020 detector. 2020 is 20 centimeters by 20 centimeters. This resolution phantom, the actual line pair phantom, is only 5 millimeters. So we had a lot of magnification. You can see here, this is the detector. If you just look at one of the imaging lines, the detector is inside this cowling here. This is where the sample sits, the end of this tube, and this is where the source is. So the sample is really close to the source, and there's a really long imaging distance, so that's high magnification. This is a vacuum tube. The reason we had that is because X-rays are scattered by air. And so if you've got 3 meters or so of air to go through, that's going to scatter your light, it's going to blur your image. And it's also going to take away some of the brightness. And we wanted to do really high-speed dynamic imaging, and so we put them in there. It goes about 10% extra flux onto the detector. Our flat panel had a 1024 by 1024 pixels, so 1 megapixel, and they were of a native pixel size of 194 micron. The spot size, this allows us to control the spot size on this source. It's a research source, and the effective spot size was 40 micron by 20 micron. So it was 40 micron high, it was higher than it was wide. Okay. So spot size determines our resolution, similar to a sort of diffraction limit. We get that blurring that I mentioned, so that's penumbral blurring. So that limits our resolution. Now, we also have sensor resolution as well. It's still relevant, so that's why we want the magnification. So we can get a line pair phantom. It's not just sort of printed ink or etched onto card. We need something that's going to be absorbing of X-rays. So often it'll be gold kind of printed onto a plastic, or in the case of the one we've got now, it's etched. It's a silicon chip that's got sort of lines etched in it so that they're less thick. They'll allow more of the X-ray through. And I wanted to bring up that target. I don't think I have that with me. Let's here. Don't look at that. Sorry, I closed this. This guy. You can see. All right. So this is the spec sheet for the Phantom. Somewhere. Where's my spec sheet? Download the data sheet. All right. So it consists of a resin cylinder, and embedded in that, there's these 2 chips. This is a CT Phantom, so there's one in each direction, so we can test for a 3D image. We can test the resolution in those directions. Now, this is what it looks like. It's a line pair phantom. This is 5 millimeters. That's the actual chip inside there. So we can see we've got different line widths that relate to different line pairs per millimeter. That's the resolution. And remember, we're going to image this and we're going to say, okay, what can we still see and what lines can we still differentiate? And that's going to give us the limit of our resolution. Now you can see this 5, 10, 15. That's the chip inside the resin tube. We have this table here which tells us what all the bits are. All right. So let's go back to this guy. And we'll have a look at an image. Okay, so this is an image that we took. You can see the tube. This is the background. The background's light because this is measuring the amount of X-rays that are coming through, and there's not much attenuation in the air here, so that's bright. We have the resin, which is, not too attenuating, so we get a little bit more through there, and then we have our chip here. These are of the same material. There's one horizontal and one vertical. This one's darker because you've got to go through a whole lot of thickness, which is going to absorb more. You can't really see very well there, and that's because of the bit depth. So there's not much contrast. The difference between a light, this light bar here and the dark bar is about, like, it's a few millimeters of material. So it's not a very big difference. Now, I've drawn this line here, just in image J, and I've measured the distance in pixels here. What's that going to allow me to do? So now I can measure this side here. I know the size of this is 5 millimeters in real terms, and I know that the pixel distance of that is now, whatever this is, that minus that, which is 304. So this will allow me to calculate magnification and effective pixel size. We can do this for optical imaging as well, and this is how we might determine our magnification. You can kind of put a lens on, you can set it up, but you can never measure distances perfectly. And if you need to know, if you're going to use this to actually make a measurement of something, you need to know exactly what your magnification is, down to a few decimal points. So what we can do is take a picture of something that we know the size of. We know the size of this, it's 5 millimeters. And then we can measure how many pixels it is. It's 308 pixels wide. And the native pixel size we know is 194. So then we can use our equation, which is native pixel size. So we can just use this equation here, which is the effective pixel size would be the real size divided by how many pixels it is. So each pixel represents 16.23 microns in the image. So that's pretty nice. It means that if we have an image of something, we can now determine the exact size of anything within that image. We can also determine the magnification by using the equation of native pixel size divided by effective pixel size. It gives us about 11.95 times. So we've got about 12 times magnification here. And that's purely due to the geometric magnification. Cool. So that's just some calculations that you can do, and we can do this for any sort of imaging, not just this imaging. What else would that allow you to calculate now that I know this? Source sample distance, sample detector distance as well. And you'll do that in the prac if you decide you want to do it. And, getting your head around this might be worthwhile for you to be able to do. So now I can zoom in. I can adjust my contrast a little bit. And so I've zoomed in on a section there. Doesn't come out very well here, but this is what we get if I zoom in and I adjust my contrast, so I can see those line pairs. Now, some of those line pairs you can make out, some of them you can't, and so this can tell us our resolution. So we have, these ones here are 50 micron vertical line pairs. We can't really see them, so they're below the limit. So our limit would be the 100 micron, which is these ones. Now, sorry, I pointed that here, these ones here. So these ones, not visible. These ones are visible. It can tell us our resolution. Now this will tell us our vertical resolution. This is the resolution in the vertical direction. So 50 micron horizontal line pairs are there. We can see them. So our horizontal resolution is different to our vertical resolution. Why is that? Of the spot size is different. Exactly right. The spot size determines really the resolution here. So we know that this is limited by the spot size because we can see it here, so it's not the sensor resolution. The sensor's got isotropic resolution, the pixels are square. But because our spot size is higher than it is wide, we have a higher resolution in that width. Usually you wouldn't take an image like this, usually you'd have a circular spot. But it just is to demonstrate how spot size affects resolution. These are 25, we can't really make them out. Alright, so that's the hour. And come back and talk about absorption, and then also talk about applications of X-rays, and then we'll go into ultrasound. Cool, so maybe we'll take 4 or 5 minutes, come back at 3. Thanks. All right, I might get started again. A little bit to go through. Okay, so now you know how X-rays are generated. Thanks, guys. You know how they're detected. So how is an image formed? Well, Coolidge told us it's like a shadow, which is true. So diving in a little bit deeper than just that it's a shadow, essentially we have different attenuation of tissues. So different tissues will attenuate X-rays more or less. And so if you have more, then you'll have a darker shadow. If you have less attenuation, you'll have a lighter shadow. This follows Beer's law. Now, in Beer's law, we have the intensity of the beam at a distance into the substance. So this is as it sort of L is the distance in. For an incident beam, we have, or an incident intensity, we have an exponential relationship. And the exponent is dependent on the length. So that means that if you have a thicker sample, it'll attenuate more. And also it's dependent on what's called the attenuation coefficient of that material. And that's just a coefficient of how much it absorbs. So how much X-rays transmit through the sample at a certain point will be dependent on the attenuation coefficient and also the thickness. Now the interesting thing is that attenuation coefficient is energy dependent. So higher energies usually mean lower attenuation coefficient, which means less attenuation. And this is why there's sort of paradoxically a higher energy radiation is often less dangerous because it just passes straight through, just goes straight through. Whereas a lower energy might be absorbed into your body, causing these free radicals, etc. So let's look at some attenuation curves and think about some practicalities for imaging. So bones are one of the, that was the first kind of medical imaging that was done with X-rays. Now we have, here is a attenuation plot. So the vertical axis is attenuation coefficient and the horizontal axis is the energy, the X-ray energy. You can see as the energy gets higher, the attenuation drops off. As the energy gets lower, attenuation is higher. So if you have a lower energy X-ray, it'll attenuate more, it'll be absorbed more, and you'll have a dark shadow. The energy is higher, much more of the X-rays pass through. This has two curves on it, one for bone and one for soft tissue. And what you want to do is get some contrast. So you want a difference in attenuation between the soft tissue and the bone. And so there's some sweet spots here that give you that attenuation. Now remember I said that higher energy radiation might be more dangerous because it's might be less dangerous. Well, that's true. So you might think we might want to go here, but that's going to, it's going to attenuate more. So you have a darker shadow overall, which means you'll need a more sensitive detector to detect it, or you need to put more flux through. But also, it will make more deposit in your body, so it'll absorb more, and then you'll absorb more energy, and it's a higher dose. So probably for bones, we want to image about here. You can see there's really good contrast between bone and soft tissue through a wide range of energies. So if we're going to pick an energy, we might pick this one here. Maybe I think that's something like 20 kiloelectron volts, and we'll get a lot of difference in attenuation, and we'll get a lot of contrast between the bone and the soft tissue. This is why bone imaging is pretty nice. So here's some examples. A break. You can look at broken bones. Anyone broken their bone and had an X-ray? Yeah. No. Now, this one's probably pretty bad. Dislocation. When your bone is dislocated, it's not in the right location, and that's a thumb there that's been dislocated. And also implants. What do you note about this implant? It's really bright. That's because it's a lot of attenuation. So this is made of steel. It's pretty heavy kind of atoms in there, which are going to absorb a lot of they're going to have a high attenuation coefficient, and so they're going to absorb a lot. Now these are negatives. These are different to the image that I showed you before. And this is often what we'll get from a medical X-ray, and that's a legacy of the film era. So even though these might be digital images, often they're inverted compared to the other ones, so that this shows more about attenuation or density rather than transmission. So the previous image had a light background because it was showing you how much X-rays were coming through. This is a negative, so it's showing you how much X-rays are absorbed. And doctors are used to seeing this sort of thing because that's what they used to get with a film. So now we sort of, well, when you give a doctor a digital image, you'll usually do the negative. So bone imaging, pretty good, pretty high contrast. There's a lot of contrast between the bone and the surrounding tissue and the air, so we get really nice images, really useful for looking at like a break or something like that. They'll set the break and then they'll check that it's fused back together properly, all that kind of thing. Mammography is another big use of X-ray imaging. Mammography is screening of breast tissue for cancer or suspected cancer. These are some attenuation curves. We've got blood, breast tissue, and calcium. The reason I put blood in there is because tumours are highly vascularised, so they have a lot of blood vessels, a lot of blood content. And so we're looking at contrast between blood and breast tissue. We have calcium here as well, because that's another thing that we look for, calcifications. Calcium is a pretty dense sort of atom or compound, so we get this kind of higher attenuation. There's still some contrast between the blood and the breast tissue here. Breast tissue, I guess, is pretty fatty kind of tissue, which is lighter than blood and less absorbing, and so we can get some contrast there. But usually we want to go a bit lower energy to really up the contrast level. And this is some examples of some mammography images. Where have I got my... So BI-RADS is like a rating of sort of risk or concern. It goes up to 6, I think. BI-RADS 1, 2, 3, 4 mean that we probably want to follow it up, but it's probably okay. So you can see here some of this sort of denser tissue, which they are kind of they get concerned about a little bit, but there's sort of diffuse dense tissue. It's probably benign. BI-RADS 4 is starting to get, obviously a bit more heavy there. This pretty obvious cancerous mass. So that's definitely going to be followed up, and I think that's like a BI-RADS 6, and so you'll get a biopsy and lots of follow-up treatments and see if it's malignant, blah, blah, blah. And this is calcifications here. They're usually okay. These are pretty small ones, but there's certain patterns, spatial patterns that will concern the physician there. So here's some examples. Now, this is screening, and I just want to talk a little bit about screening because screening is an interesting topic in terms of imaging. So one thing about these is it really requires an expert to view them. It's not kind of like, you've got cancer, you don't have cancer. There's kind of, a bit of subjectivity there, and you need expert radiologists to review them. And essentially, that training is just looking at a whole lot of different pictures and being told what they are, and then you kind of learn to see what things are. There's research into computer-aided diagnosis. These are usually due to regulatory issues. They're usually more of an aid to a radiologist, so it might sort of circle a certain area and say, look, maybe you want to look at this one. But the decision-making will still come down to a person at the end of the day. And that'll be like that for quite a long time. Even with like AI and all that kind of thing, it's still a long way off trusting a computer to make your diagnosis. Now, screening carries inherent risks, and there's always debate with any screening. So screening is basically when you just image a whole lot of people because everyone's at risk kind of thing, and hopefully you'll pick something up early. So you'll image people who have no real symptoms or indication of disease in the hope that you'll pick something up early and we'll be able to treat it. Now, the problem is with that you can get overdiagnosis and overtreatment. So imagine you go in, you have a sort of something like this. Like, it's probably okay, not sure. Why don't you go in and have a biopsy? Okay. So then you've got to wait for the biopsy, and you're sitting there thinking, this isn't so good, not so crash hot. You've got a lot of psychological stress. You're going to have to go and get a biopsy. It's going to cost you money. It's going to cost the healthcare system money. And most of the time, it turns out to be benign. So most of the time, it's okay. And so that's a huge cost just because of this screening. And false positives are a huge problem in screening, and often they outweigh the true positives. You can also get overtreatment. So say you see something there, and look, this is kind of cancerous. Okay. Now, maybe you'll go and have that removed. Maybe you go get some kind of chemo or something. But there's a chance that that would never have grown into something that would be life-threatening. And so that's overtreatment. And that was only picked up because of this screening program. So that's no good as well. They did a huge lung cancer screening trial in Europe, and the false positive rate was 96%. So 96% of the positives were false positives. In addition, this was a CT screening trial. So CTs have quite a lot of dose, and they estimated that they caused something like 1 or 2% of cancers or something like that. So people were getting cancer because of the screening. In the end, there was a small benefit to people who picked up true cancers and they treated them. A lot of the cancers were overdiagnosed and overtreated, so basically they would never have grown to a problem. Often you'd go get a biopsy, it's benign. But there was some benefit overall. In the end, they decided not to implement it. Why do you think that was? Come on, uni students, money. It's just too expensive. They can't screen all these people. They couldn't afford it. They said, look, the benefit doesn't outweigh the cost in money. Also, there were these other issues, but that's screening. So screening's kind of, it's cool, but there's always these issues. Also, there's demographic issues as well. So if you think about screening, what age do you start screening at? If you're younger, you've got more time to develop cancer. If you're quite old, then look, this isn't going to give you cancer because it's not going to be the thing that gets you. So there's all those things. Okay, so that's for those two applications. Now, let's talk about contrast agents. What if those two attenuation curves, what if there's no difference there and we can't really see any contrast due to attenuation? So sometimes there's not adequate contrast. Sometimes the tissues just absorb in a very similar way and we can't see a difference. So we can use a contrast agent. Usually these are iodine-based, so sort of a pretty heavy element, and that will be introduced, usually for vascular imaging, also for gastric tests. I'll show you some examples. And so these are introduced into the body, into the bloodstream, say, and that makes that more dense, and that means that we can see it, we can differentiate it from the surrounding tissue. It also can give us some functional information because now we can see the flow. If we introduce it and we do a imaging as it's flowing through, we can now image the flow, which is part of the function. And so it can give an indication of like circulation and diffusion, whereas an actual just looking at an image might not give you that. So this is attenuation curves for soft tissue and blood. You can see I've made the red one a dotted line because they're basically just the same. They're both essentially just water. And so there's very little difference in attenuation. We can introduce a contrast agent, and we get iodine. An iodine contrast agent. This is an attenuation curve for iodine. You can see like a huge contrast, huge difference there. What do you think these little bumps are related to? So I mentioned at the start that absorption of photons is dependent on the electron shells. And so these relate to specific energies of gaps between electron shells that are more, so you can get these jumps in absorption because we can open up new shells that we can absorb. Okay, so this is called angiography when we use a contrast agent in blood. So we can evaluate blood vessel health. Here you can see stenosis. You can see there that there's no blood there. That's a blockage in the artery. Aneurysm is the opposite when you get like a weakness in the wall and it blows up into like a balloon. And we can also assess the effectiveness of treatments like angioplasty and stents. Angioplasty is when they insert a little balloon into your vessel to unblock it, to open it up, and stent is when they put a little tube in there. And so we can put the tube in and we can see, hey, did that actually open up the vessel? Do you now have blood flow downstream? Here's an example. So this is the blood vessels within the heart wall, and this is a problem that people with heart disease often get. And you can see here we have a stent was put in here, Again, a stent is like a little tube to help keep that open and remove the blockage. Now that stent has disrupted the flow in there, and also it's introduced a foreign body in there, and so it's sort of started a thrombosis. And this is often a problem with stents. You get thrombosis and you get a blockage. So you solve a blockage, but then later on the track you introduce another blockage because of the stent. And this was made visible by the iodine, this dark kind of, you can see this is much darker. We get that contrast of the iodine contrast agent. Here they've done a balloon angioplasty to open up that thrombosis, which was here, and you can see now, we do the intervention, we can now see the sort of the increase in flow through here. We can say, well, that worked, I guess. Yeah, I thought the same thing. It took me a little while to figure it out. So this is your heart. I believe it's a nipple. It took me a little while as well, actually. I think it is anyway, I'm not sure. Cool, so let's look at this one then. This is a video showing that in action. So this is an angioplasty with a stent placement. So little balloon, open it up, put in the stent. So there's the blockage there. This is a fluoroscopy, so it's like a video. You can see they inject the bolus of contrast agent and it just lights up all those vessels and continues to pass through. That's the stent they're putting in. They slip it in the artery with a little wire, and they do this all under the X-ray so that they can see what they're doing. So that's why you can see it's a lot of dose, because you've got they can expand it. It's like an expandable with a balloon. Not sure if Sean talked much about stents, but now you can see that the flow there is vastly increased, which we can see because the contrast agent, or the density there is much higher. So there's more flow going through there of that contrast agent. Tells us there's more flow. And this wouldn't really be possible without being able to see what you're doing in there with the X-rays and the contrast agents. Very difficult to place that in the right spot and all that stuff. Yay. All right. So another thing we can do with this sort of thing is, this one's called a barium swallow. And there's a lot of these sort of gastric... Have I got my thing? Where do you go? Sorry about that. There's a lot of these sort of gastric imaging done. And essentially... if you want to look at how someone's swallowing, how things are going down their esophagus and into their stomach and that kind of thing, or how they're passing food through their gastric system, you can give them food, drink, which is laced with a contrast agent, and then image them. And that's not working for some reason. I'll just put that into my browser. It's not a link for some reason. About that. You should be able to get these through the slides, but this is the one that's got sound as well.
Okay, I just want you to look straight ahead of the wall and say...
No, it's not sounding too good, actually.
Okay, I just want to look straight ahead of the wall and say, candy.
Oh, yes, cool.
This is very important, but it's going to take 1 sip and swallow.
Where's the sound? So you can see they're giving them drink and then like a porridge, and that's got barium in it, and that allows them to see how they're swallowing. These dead times is because they don't want to be imaging when there's nothing happening. So, sorry, I should put a trigger warning on this maybe, but yeah, so they can see it sort of going down, they can see it if it's getting stuck, and if you could hear it, which you can if you watch it at home, they're saying, how does that feel? I feel like it's stuck here. Well, is it stuck? They can see if it is or not. You can see how your swallow is working, all that stuff. We get to something, so now it's getting thicker, and they can see how thicker food is going down. They turn them to the front as well. Yeah, this one's good. The vocal cords there. And you can see he's sort of getting stuck there. So this is like a porridge, I think, that's getting stuck. Anyway, you get the idea. Cool. And they can look at, yeah, so they can see it going all the way down and how it's entering the gut and all that stuff. I mean, swallowing's a big kind of part of your life, really. If you can't swallow properly, it's not very fun. So, all right, so that's some contrast fluoroscopy, and there's sort of some of the main kind of fluoroscopy examples. So that's imaging, planar X-ray imaging. I'm not sure if you've heard of CT. CT imaging is when you do 3D imaging. And the way that works is by looking at X-ray images from different angles. So I've got angles all around. We take pictures from all different angles, and from that we can build up a 3D picture. And I've just got some gifs here of this. So this is a CT scanner. So essentially what you do is you lie in a bed. This is on a bit of a robotic stage. You get put into the donut. And this has got a source on one side and a detector on the other, and it's all in a big bearing which spins around super fast. And so I can take images from all different angles, and you can build up a 3D image. Now I've got this which shows it rotating. This is one of the fastest CTs on the market. It does a rotation, so it can take a 3D image in 5 seconds. So you see in there's the source and the detector. Might be able to catch it, but a whole lot of other electronics. This is exploding. So pretty advanced piece of engineering. And the reason they've put all that effort in is because, I mean, it's just an amazing piece of imaging technology. You can look inside in 3D at high resolution. So this is how, basically how CT works. You take projection images, so think of this as a slice, and you do these slices all the way through. So this is an integration of the intensity of all the, of the absorption of all that is within here. So it's like a projection, a shadow. And you take that at every angle, and you can. This is just that line placed, sequentially, and that's called a sinogram. So that's acquiring the image. You get a sinogram. Remember, you don't know what this is. This is the person lying here. You can't see inside. And so you get this sort of sinogram here. So this would be for one slice. It's just one kind of plane of the internals. Then the next thing to do is to back project. This is just showing back projection of each forward projection in turn. So the idea is just basically you smear that back across the reconstruction space. And if you do that, and rather than just showing you this one smear for each one, you actually add them all together. And with some filtering, you can reconstruct what was the 3D space, the internals. That's the basics. So I used to go into the details, but I'm not going to go into the details. That's basically how CT works. And this is some examples of medical CTs. So here is just through the abdomen. You can see these are the ribs. This is like the liver, I think. Spine here, muscle, skin. This is part of the table. So this is a slice through this way. I mean, super useful for sort of doctors. This is an example of this is through the lungs, and this is called a pneumothorax, and that's when you get air in between your lungs and the rest of your chest cavity. This is all meant to be sealed up, and that's what's holding it together, is that it's basically sealed. You get a little bit of a gap in there, you get some air in there, your lung collapses, and that's what's happened here. So complete collapse of the lung, this is all air, and that's called a pneumothorax. And this is maybe what they're going to fix it with. They put a little tube, they suck out all the air, seal it up. Not quite as serious as you would think, but yeah. But you can see the power of this, and this is planar, so you can get one of these in every slice. You can get a full 3D image of what's going on inside the body. Super useful for a whole lot of things. All right, so that's X-rays. I've got some slides on ultrasound. It's much less than what was on X-rays, so we'll go through this now. Ultrasound is probably the next most commonly used modality, aside from MRI as well. So this is an ultrasound. You've probably all seen this. Someone you know has had children, your parents, also probably some other family members or friends. And this is what they'll show you. My baby. Okay. So this is the baby in utero. And this is one of the main uses of ultrasound. And I've got some fun GIFs here. So essentially, how does it work? Ultrasound is sound pulses, so pressure waves. The reason they're called ultrasound is because it's a higher frequency than our ears can hear, so 20 kilohertz plus. And usually it's higher than that even. So you send a little pulse, a little sound pulse in, that goes into the body. It'll be reflected off different interfaces within the body, and you get an echo back. Similar to radar, you think probably can picture radar, it's a similar thing. You send it in, it comes back. At each interface there'll be a little bit reflected, and so you get multiple echoes. The time it takes for that echo to come back is the distance. Time of flight gives you the distance. The strength of the echo tells us about the different materials. And also if there's a frequency shift, it tells us about the speed of the material. We'll go through a bit of that soon. We have a transceiver, which is both transmitting the pulse, the ultrasound pulse, and also receiving it. So it can hear it, it can read it, and also send it. And we sweep this across, like electronically, sweep it across the field of view to build up a full picture. This is an example. You can see you can't see it very well, maybe in the next one. So this is basically how it works. We've got the transceiver, it sends a little pulse. That pulse echoes off the interfaces of the object. And then we can read those here, back at the transceiver, and the time it takes from that first pulse for the echoes to come back tells us the depth of those interfaces. So then we can just put a little, that pixel there can be made bright to tell us the depth and build up a picture. So the transceiver is called that because it's both a transmitter and a receiver, and these are made up of piezoelectric crystals. Hopefully you all know what that is, but essentially it's a material which, when you deform it, if you compress it, say, it will create an electric potential, it will create a voltage. And if you, that should play, that's not playing, that's fine. And if you strain it, if you deform it, it'll give off electric potential. Also, if you put an electric potential across there, if you put a voltage from one into the other, it will deform. So we use this to make a transceiver. Put an AC current in there of a certain frequency F, it'll cause it to expand and contract at that frequency, creating a pressure wave at that frequency. And that's our transmission, so we can create a pressure wave using this piezo crystal. Then when that pressure wave comes back, this can act like a little microphone. The pressure wave will slightly expand and contract the, it'll induce a deformation in the crystal, and that'll generate an AC voltage, which we can then read with electronics. Now, just some basic acoustics. When a wave interacts with an interface, some reflects and some transmits. And the total energy is conserved, and some of that wave will bounce back, and some of it will keep going through, maybe refracted. If there's another interface here, again, some of that will bounce back and some of that will refract through. And the amount that's reflected is determined by the difference in impedance. It's called impedance, acoustic impedance, of those two materials. And that will tell us how much is reflected. So the take home there is that if you have a difference in impedance, that will give a reflection, and a greater difference in impedance will give a greater reflection. And so if you have a very large difference in impedance, then your transmitted wave will be very small, and you'll get most of it will just bounce back. So here's some common acoustic impedances of some materials. Air is 0.0004 milliraves, and fat is 1.34. So sort of a 3 order of magnitude difference there. This would give us a reflection coefficient of 0.999. So basically everything will just bounce back. If I shoot an ultrasound pulse at you through the air, it was just going to bounce back. None's going to actually enter. So we can't really image very easily unless we do some impedance matching, and so that's why we use this gel. And that GIF is just saying, I'm just going to put some gel on you. If you've ever seen an ultrasound, they squirt this usually warmed gel, and then they use that, and that provides it sort of takes away any air gap between the transceiver and the body, and tries to match the impedance of the fat, and so you can just send that pulse straight in without having it to go through air, bounce back. Also, this is why we can't image through lungs. There's many air tissue interfaces in lungs, and so you just get reflections back. You can't actually go very deep. They do some, but it's just scattering everywhere. You can't really form a true image. So that means you can't image through the lungs. If you want to image the heart, that becomes difficult because it's sitting there within the lungs. So the attenuation, there's attenuation as well. As that sound travels through any material, it will start to attenuate. You'll lose power, and that is dependent on the attenuation coefficient and the path length. So this is following Beer's law and also frequency. Note that this is a dB scale, so this is a logarithmic kind of scale here. That's why it's not an exponential, but essentially you have a frequency-dependent attenuation. And it's also dependent on the path length and the attenuation coefficient. So if I want to penetrate deep, if I want to image through a lot of tissue, like a pregnant belly and through a baby's head and everything, that's quite a lot of path length. And that means that there's a limit to the frequency I can put in there. So you need a relatively low frequency. Now, the problem is frequency determines spatial resolution. So if I want a lot of penetration, I have to have a low frequency of my ultrasound pulse. So the sound wave is a low frequency, so, and then that means that I can't accurately time it because you need a full wave to send a pulse. You can't just send it. So if I have a low frequency, I need a longer pulse, which means I can't accurately time the return of that pulse, which means I can't accurately locate the interface, which means I have a lower spatial resolution, basically. So there's a trade-off there between frequency for penetration and frequency for resolution. So there's a limit in resolution if I want to penetrate deeply. If you are looking at something at the surface, or if you're looking at something small, like a small animal, you can then have much higher spatial resolution. than if you want to look at, say, a baby in utero. So there's an inherent resolution limit, and so most ultrasound is, you consider it low resolution. All right, so the main sort of application of this is obstetrics. This is 1960, and this guy, Phillips, I think his name was, Dr. Phillips, he sort of was the pioneer here. This is a 1960s ultrasound system. See, pretty large. This is probably like a projection screen there to look at. This is the thing driving it. But super safe, no radiation. So you don't want to be X-raying fetuses really, and so really useful for obstetrics. This is a modern machine here. Pretty portable, reasonably cheap. You can pick something like a sort of a base model of 20k CT machine, millions or hundreds of thousands anyway. Often an obstetrician will have one of these in his consulting room, just in his office. He just pulls it out, puts the gel on, has a look. And also portable, so you can sort of wheel them around the hospital. So really useful in obstetrics, and there's a whole lot of things that they look for. If you have a baby, anyone have kids? No? I've got 3. Did a lot of ultrasounds. So you go in, you do maybe 1, 2 or 3 scans throughout the whole pregnancy, and at different stages, and they're looking, initially you're looking for a heartbeat on a little embryo. You can't see it, you see a little dot, but you can measure the heartbeat there, so you see there's something live there. You can estimate the age of the pregnancy, which is important for estimating the birth date, which is important. Evaluate the position. Is it breech? Is it that means feet down, or is it sort of posterior, turned around? Evaluate the position of the placenta. If that's covering the opening of the cervix, you've got to, that's no good. See if you've got twins or not. Pretty important. All these things. And fetal growth, so make sure that the fetus is developing as it should. Here's some examples, and this is all done sort of live, so it's very operator dependent. So you have someone sitting there, they're taking images, and they're drawing on the screen, basically marking between 2 points with a cursor to measure, say, the head circumference, or the femur length, which is can help you date the fetus, so 20 weeks and 1 day there. This is all coming up on the screen and recorded for the doctor, and that's the femur is 3 centimetres. So all this stuff. Other things that ultrasound can be used for, and is often used for, is looking at things like kidney and gallstones. So this is a kidney stone here. You can see it lights up pretty well. They're pretty dense, and so the sort of the impedance is quite different to the surrounding tissue, and so you get pretty good images. Gallstones, looks like it's in pretty bad shape there. So go in, you have some side pain or something, they see gallstones here. They can try to break them up with ultrasound as well. They can put some high-powered ultrasounds in there, or they'll just remove your gallbladder. All right, so that's just standard ultrasound imaging. They can also use what's called the Doppler effect. Has everyone heard of the Doppler effect? Yes? So this is how they determined that the universe is expanding, because all the light coming from them was shifted to the red. You might have heard of redshift, which means that everything's moving away. The frequency of the light coming back, or coming from the sort of faraway galaxies and stars, was shifted to the red, so it was moving away from us. Also, it's the same thing that causes a siren to sound, higher pitch when it's coming towards you, and then lower pitch as it moves away. Essentially, the sound waves are bunched up at the front of the source in the direction that it's moving. So you've got a higher frequency here of sound waves for a moving source, and a lower frequency behind compared to what it's actually emitting if it was stationary. So we can use this to determine if what the echo is bouncing off is moving, and the speed of that motion as well. Don't have to worry too much about this, but go through the maths in your own time. Usually we're looking at blood here, and so essentially the frequency shift between the emitted pulse and the echo will tell us, or can tell us, the velocity of what the image is doing. Velocity would be, for example, how fast the blood's flowing. And so the frequency shift between the emitted pulse and the echo, so we send a frequency in, or a pulse of a certain frequency, it comes back, the frequency is slightly different, shifted. And that can tell us, and that's because of the Doppler effect, and that can tell us the velocity. So here's some imaging, Doppler imaging examples. You can see how useful this is. So this here is, can anyone think of what that might be? It's an obstetric image. Yeah, it's the umbilical cord. So we have red is flow towards us and blue is flow away from us. An umbilical cord is like a twisted kind of spiral with, you know, an inlet and an outlet. So blood's going to the fetus and blood's going away from the fetus. And this is what we want to see. We can see that the flow is really important, that there's adequate blood flow from the mother to the baby. And that can tell us that. If you can imagine if that wasn't coloured like that, you wouldn't be able to tell what the flow is doing. You'd just be able to see that there's a cord there. This is a renal colour Doppler, looking at flow within a kidney. It's pretty important. You know, you can get blockages and thrombosis in the kidney. If you have high blood pressure, you might get one of these to see if there's problems in your kidney, because that sets your blood pressure. And you can have echocardiograms as well. You know, obviously heart disease and all that kind of thing is pretty important. You can use this to test LVADs as well, I think, and sort of certainly if you're getting an LVAD, you're getting a lot of echocardiograms. Cool. So that's basically it for today, and that's it for me. Next week, it's not playing. Come on. Next week is the break, I believe. Then we have some guest lectures. Andrew Stevens will be giving a lecture on instrumentation in medical devices. Kay Morgan will be talking about phase contrast X-ray imaging and synchrotron imaging in particular. And then week 10 is going to be a really good one. Kishan, who runs the Monash Generator, which is the Startup Accelerator program, will be talking about how to pitch. And that's going to be really good because you need to do your pitches in week 11 and 12, your 3-minute pitch. So he'll give you a lot of good tips on how to formulate that. Cool. Thanks very much. Thank you. That's very unnecessary.
When we were showing the graph between the bone and the soft tissue,
Yep.
So there were a few, I noticed there were like 2 spikes.
Yep.
Is there a reason behind that?
Yeah, so those are, let me bring it back up. Those are due to the, so that they're because, so yeah, we'll go to there, this one. This one? Yeah, so these here. So they're because of the way the materials are absorbing, the atoms absorb the photons. So they're similar to the K lines, or the characteristic radiation, in that sense, in that they represent this energy here is an energy gap between 2 different things. So at this point, once you hit this, you have a lot more ability to absorb, because you've got electron shells which have that gap.
Okay.
So you can absorb more of that energy at that point, which gives you a bit of a sort of discrete bump. Yeah, so usually, often we'll do you can do some interesting imaging where you can just shift your energy a little bit. So especially on the synchrotron, we can get an imaging which is just, sorry, which is just very monochromatic, so just one single wavelength. And you can image sort of one side of that and the other side, and then you can get this contrast because you've got such a big absorption after that little peak in the other one. Yeah, that's pretty cool. Yeah. Hi.
Regarding the assignment.
Yeah.
So the next stage of the assignment will be more about the device that we're going to make.
Yeah. So the next stage, and I'll put up the information before Friday.
So that's what my doubt is. Can we right now we don't expect very detailed.
No. So
It just has to be.
it's more about the problem than the device at the moment.
Standards and
Yeah, and then kind of what are some issues we have to
Yeah. Yeah. Yeah, we do. I don't know how many she ran off. Are you happy if I help you get started and then come back at the end? Are you going to go straight home?
No.
Okay.
Yeah, even, I mean, collecting papers isn't a big deal.
All right, perfect.
Just get the ball rolling.
Yep. All right, great. We'll collect the papers that aren't being used. We should collect, because otherwise we can't roll out for the sub-exam.